Welcome learners. In today's lecture, we are going to continue our discussion on electrostatic charges and the effect they have if they are in the vicinity of another charge or in the vicinity of an electric field. So today's topic is on electric field intensity. So we are going to see what is this phenomena of electric field intensity. Before we continue, we want to first understand the behavior of charges, if it's a positive charge or if it's a negative charge. So how does it radiate in free space or in a spherical universal coordinate system? So let us assume if we have a positive charge Q and on the other hand we have a charge with a negative energy or a negative charge Q. So whenever we have a positive charge, the standard is that it is always going to radiate energy outward, and it is represented by these arrowheads. And you can see that these radiations are uniformly and evenly spaced. So whenever we have a positive charge, we consider it to be a source, and it is radiating energy or field lines, as we are going to call them later. So these are the radiated field lines from the positive charge or a source charge. You can see if we have a point source charge or a positive point source, the energy is radiated in the outward direction as represented by the electromagnetic simulator's animation image. Similarly, if we have a negative charge or a negative Q, we assume that it is a sink. It is basically going to absorb the energy. So it is represented by a negative sign and the arrowheads are inwards, or it is getting absorbed. So the charge is basically getting absorbed and it is again uniformly or evenly distributed electric field lines. The animation of this negative point charge is also showing the same, that it is taking or absorbing the energy in the form of field lines that is entering into it. So this is an important representation that we need to remember, that how the electric field lines are when we talk about point source charge or point sink charges. So now let us continue our discussion and understand what is electric field intensity. So first we are going to write the generic definition of this electric field intensity, and then we are going to understand that how did we reach to this definition. So electric field intensity basically gives us the magnitude and direction of an electrostatic force. So remember, this chapter is talking about the electrostatic charges, so the force generated by them is the electrostatic force. So electric field intensity basically tells us the magnitude and direction of an electromagnetic force or electrostatic force, to be precise, that is applied or that could be or would be applied to a point charge. So this is an important word, a point charge residing inside that field. So we already know about what are fields. That can be scalar or a vector field, but in the course of EMT we are mostly concerned with the vector field. So electric field intensity basically is defined that it is that quantity which gives us the magnitude and direction of an electrostatic force which is applied to a point charge residing in that field. So what is a point charge? So point charge is something that has a unity magnitude, meaning its value is 1, and normally it is just like a single point on the screen, which means that it has no length, width and height. So the point charge is something like a dot. It has no length, it has no width, and it certainly doesn't have any height. So it's just like a dot. So we call this as a point charge, which is a fictitious charge. So this is what the definition says, but let us see how we can further understand it. So let us first start with the electrostatic force. And see what are various kinds of. So there are two kinds of electrostatic force or the fields generated by the electrostatic charges. The first is the electric field line or lines, and the second is the result from the electric field lines and topic of our today's discussion, which is the electric field intensity. So now what is electric field lines? To put it simple, consider you have a torch, and the torch is obviously going to have a source at this end, and output of this torch is in the form of light, and this is surrounded by a medium which is air. So the source can be wired or wireless. So this is the battery. Now when we look at a torch, we can see that there are light rays coming at the other side or the output of this lamp. So these light rays can also be translated as field lines or light field lines, because we can from some angle look at these lines coming in this direction. Similarly, if we take an example of a water pipe, so we know the one side of this water pipe is an inlet and the other side is an outlet, and the water is moving in the form of what we call as water waves. So these waves can also be treated represented as water fields or water field lines. So this is something that we can portray whenever a water is moving inside a pipe, and we can say that the water is flowing with certain orientation, a certain frequency, but at the output we can assume that these are certain water field or water field lines, although the output is a continuous flow. But if we can manage to disintegrate that water flow into different wavelengths or the frequencies, we can segregate them into different waves as shown over here. So these are certain examples of how the field lines may be imagined, especially when we are talking about the charges and the energy they radiate or they absorb, which means that if we come back to our charges which we just saw previously, so if we have a positive charge, then we know that it is uniformly generating the field lines, and these are the electric field lines for the positive charge. And if we have a negative charge, then the field lines are being absorbed by this charge over here, and they are all uniformly distributed. So these are the concept of the electric field lines. Similarly, if you want to have a symmetric distribution of field lines between charges, so we can also have that. So we can have a symmetric distribution of field lines, and we can have an asymmetric distribution of field lines. What does it mean? So let us say we have again two charges. So this is positive charge Q and this is negative charge Q. We know that the Q charge, if it has the same magnitude as the negative Q charge, the field lines when they are close together will be along the line. So this is the flow of electric fields from positive Q to negative Q, and if the distance is increased, the same lines will follow a curved path. This is what we have seen by the analysis provided by the Coulomb's law. So this is like a symmetric cylindrical formation of the field lines. Similarly, if we have asymmetric lines, so for the asymmetric, again if we have charge Q and Q with a negative, so let's say this time the charge Q has a value of magnitude greater than negative Q. So in the beginning, if the charges are close distance, the field lines will travel straight, but as the distance is increased, they will go in a curvature or a cylindrical form. But after some time, since the magnitude of the positive Q charge is more than the negative Q, it might bypass these charges in the form of the field lines. So the field lines might bypass these points. So this becomes a non-symmetrical field line distribution. So this is how the electric field lines are. Now let's talk about why we have electric field intensity with us. So for the electric field intensity, let us consider the same charges with the same magnitude, and we know that the field lines are moving as such. And now once we know that there exist some field lines, we are interested now in order to find what is the specific strength of a field line at this point, what is the strength of the field line at this point, at this point, at this point, and let's say at this point. So the phenomena, or the way we want to figure out the strength at a certain point on a field line, this is known as the electric field intensity. So electric field intensity will be what that we, so for example, if I want to find the strength or intensity of the field line, or the electric field line to be precise, at this specific point, then this phenomena will be the electric field intensity. And again, we represent this by drawing certain tangential lines appearing from this field. So in order to find the electric field intensity in terms of geometry, we draw some tangential lines coming out of this, letting us know that we want, or we are interested in finding at this specific spot the strength of this field line. So this is what the electric field intensity is. Again, since it's a vector quantity, so the original definition holds that we are interested in finding the magnitude and direction at a specific point inside this electric field line. So this is the electric field intensity. Similarly, one more thing to remember is that electric field intensity is not dependent as a function of time. Rather, electric field intensity is a function of space, which means that since the charges are static, they are not moving. Charges are static, which means they are at rest. So it is not dependent on time. It is not a function of time. Its value will remain the same where we want to find its intensity, but it is a function of space. So it can change its spatial location. It means that the coordinate systems, the rectangular coordinate system, the cylindrical coordinate system, and the spherical coordinate system, which we saw in our previous lectures, is the space which we are talking about. So a charge or the electric field intensity is movable in a space, but it is not going to be affected by the time. So this is an important information to know. So now let us define mathematically what the electric field intensity could be. So if we have any charge, let's say Q, and we know that it is going to radiate the field lines in an outward direction. So we know that this is the vicinity of the charge Q. And in this vicinity, if we bring another point charge, so the definition said that if we bring a point charge, let's say this point charge is represented as Q naught. Point charge is something that looks like a point and it doesn't have any form of strong energy to radiate, but it is like a test charge. So you can say it's a test subject or it's a test charge. And we bring that test charge in the close vicinity of this source charge Q, let us call this as a source point or a source charge, then this Q is going to experience a force as per Coulomb's law, and this force is in turn going to give us the electric field intensity at this specific point. So this means that if charge Q naught, a test charge, is brought in close vicinity to Q, then as per Coulomb's law, the vector representation of this could be the K Q naught. So the relationship between two charges, and K is the dielectric coefficient, divided by R square. And if you want to represent it as a vector formation, so it will have a unit vector. So this is the representation or the relationship between two charges in terms of its force. And now if we want to see the electric field effect on this test charge over here, then electric field intensity is basically the force applied on the test charge per unit discharge. So this is the force applied per unit test charge, and its unit normally is Newton per Coulomb, but we take the practical units, that is volts per meter. So this is what the electric field intensity mathematically is represented as, that a certain force is being applied from source charge to the test charge, and the electric field is the behavior or the response of the force being applied on the test charge. So we can further simplify the electric field equation into a more representable form. Is the force applied is kq q naught divided by q naught, and let's put r as an absolute square, so we get the positive value, multiplied by the unit vector ar unit vector. So this and this cancels out, so the electric field intensity in the vector form is kq divided by r epsilon naught square into, and if I write the value of the unit vector, it comes out to be r divided by the absolute of r square in volts per meter. So this is the final mathematical representation of the electric field, and the unit is written in volts per meter because in practical sense we talk about this, that electric field intensity is basically the relationship of potential difference on a certain distance. So potential applied within a certain distance gives us the electric field. That's why we are writing the unit as volts per meter. This is normally utilized when we are talking about circuit analysis. And why we are talking or giving the reference of circuit analysis, because in the beginning of this course we mentioned that circuit analysis was a special version extracted from this course of electromagnetic field theory. So we can use these notations interchangeably, but the recommended unit for electric field is volts per meter. So now we have the vector form of the electric field taken from the Coulomb's vector form of the force, and this is how we represent the vector field on a single point charge. Okay, so this is the vector electric field intensity. So let us see what the book has said. So book is giving us the same information. So again, the force applied between two charges, let's say if this is qi, the source charge, this is source point, and this is the test charge or the focal point. So the relationship between these two charges is represented by Coulomb's force, and the electric field intensity is going to be in this direction, represented by the red arrow, and this is the ratio of the force per unit charge. Again, the unit is normally represented as volts per meter. Similarly, if we have the charges not placed at the origin but at different location. So in this slide we can see that if the charge or the source point is moved away from the origin, then the electric field intensity's equation of this r square is going to be represented as the difference of position vectors or the distance vector. So if the distance of source point from the origin is rm, and let's say if p is the point where we want to find the electric field, and the distance from origin to p is r, then this r will be equal to the difference of r minus rm. So the electric field intensity, then if we have the source away from the origin as shown over here in Q, is then represented, or the equation is changed from r square into the distance vector, which is r minus rm absolute square, and am represents the unit vector, where am is basically the vector r divided by the r absolute, or it is r minus rm divided by r minus rm absolute. So this is the representation of the unit vector. So we can take an example to further understand how this can work. So let us say I want to find the electric field intensity at a point 0, 3, 4, and the charge that I have been given is of 5 microcoulomb, and it is present at the origin. So we need to find the electric field for this scenario. So how can we go about this? Okay, let us first visualize this. Let us say that we have the rectangular coordinate systems and the charge Q is at the origin with a value of 5 microcoulomb. And the point of interest where we want to find the electric field is x equals to 0, y equals to 3 and z equals to 4. So maybe it is some over here. So it is 0, 3 and 4. So we want to find the effect of this charge on this point over here. So it will have a certain distance r for the position vector r, and the electric field will be in this direction, which is E of or just we say electric field as a vector. So this is the electric field we want to find on point P from the charge which is placed at the origin having a value of 5 microcoulomb. So how can we go about this, solving this problem? So straightforward. We know that electric field intensity of a point charge is equal to the force applied on that point charge, which is equal to kq divided by r absolute square into unit vector. So what is the value of r? So r is the distance vector which is over here. So we can say the distance is, we take the point vector and subtract it from the origin value. So 0 minus 0 is 0, 3ay plus 4az. So this is the unit vector, and let's take it as a unit vector. Now if you want to find the absolute of this unit vector, so this is, you take the scalar quantity and square it, so it comes out to be 5. So finally we incorporate all of these into the basic equation. So the electric field intensity for the point charge is going to be, value of k is 9 into 10 raised to power 9 meters per farad, charge value is 5 microcoulomb is 10 raised to power minus 6 divided by the value of r absolute is 5, and you take the square multiplied by the unit vector. So the value is 3ay plus 4az divided by the absolute of r is basically 5. So this is what we get as an answer. If you want, we can further simplify it, but this will be the answer. It will, units will be volts per meter. So you can further simplify to get a simplified single value, but this is the solution to this problem. So this is when the charge is placed at the origin. But what happens if we have charges not placed at the origin, rather it is a system of charges or discrete set of charges? So it means that if we have charges not placed at the origin, rather it is distributed in space, then how we are going to find the electric field intensity, because now we are moving from a single point charge to multiple point charges. So for that case we use the principle of superposition. So for example, before we go into the mathematical analysis of it, consider this scenario. Let's say if I have a charge q1 over here, then a charge negative q2 over here, then a charge plus q3, and I want to find the electric field at this point. So how can I go about this? So I know that q1 is going to radiate energy outward, so it is going to have its effect on this point over here, and the electric field from this will be at this point. So let us call this E1. For q2, the energy is absorbed, or the direction of the arrow is such that the energy will go towards q2, so the electric field intensity for this will be in this direction. Similarly for q3, it is going to point over here, and the electric field intensity will be in this direction. So which means that in order to find the electric field at this point, we have to use the principle of superposition. So the principle of superposition basically tells us that if we have multiple sources affecting at a certain point, we can tell its total effect. So the E total, which is this point, is going to be the sum of the electric field from the first, the second, and so on. So this is the principle of superposition. Or if we have discrete system of charges inside any space, then how we can find the combined electric field effect from these charges. So this is how we use the principle. So here you can see the example as well, that if we have a charge q1, another charge q2, and this is the test charge where the field effect needs to be found. So we can see that q1 is applying a force on this charge in the upward direction. q2, since being a positive charge, is also applying force in the upward direction. So this means that the electric field for q1 will be in this direction. For q2 it is going to be in this direction. So the total electric field will be perpendicular to this, and this will be E total. So this is how we are going to find the charges. In order to find this, what information we need? So we know that the basic equation for the point charge is equal to kq divided by r absolute square into unit vector. So this is the equation to find the electric field of a single point charge. But if we have more than one charges, then we can add those fields together as such, so using the principle of superposition. So basically this is the mathematical representation of finding the electric field of more than one charges. So here we take the value of the qi, which could be q1 or q2 charge, divided by the value of k, which is 1 by 4 pi epsilon naught, and the value of r becomes now the difference of between charges. So if we are finding the electric field as the effect of the first charge q1 on this, then the value of r will be r minus r1. What is r1 and r? So r1 is the position vector from the origin to q1, and r is the position vector from the origin to the test charge. So the r dash is basically r minus r1. So here we can use that value, and this portion is basically the unit vectors equation that will have the same value of r minus r1. Similarly, if you want to find the effect of q2, then we are going to use or replace r square from this equation to r minus r2, which is basically the distance vector or the difference from the origin to q and from origin to q2, which is r minus r2. So this is where the value of r gets changed for system of charges, and then we incorporate them into this equation that gives us the sum of all the charges. So this is how the system of charges is dealt with in order to find the total electric field of multiple charges in a vicinity applying their force on a test charge as shown over here. So let's look at an example where we can further understand the effect of system of charges and see how we can apply the principle of superposition and find the total electric field at a certain point. So for this, let us take a question and see how can we solve this. So let us say, so the problem or the question statement is such. So we have a charge. So let us say we have a charge q1 having a value of negative 0.3 microcoulomb, and it is placed at a location or point A at 25, minus 30 and 15 centimeter. Then we have another charge q2 having a value of 0.5 microcoulomb, and it is located at point B having a value of minus 10, 8 and 12 centimeter. We have been asked to find the electric field intensity at the origin and at point P, that is 15, 20 and 15 centimeter. So how can we go about this problem? So let us try to solve the first part of it, and then once you understand the first part, the second part is as a homework exercise for you. I leave the answer for the second part so you can verify the solution yourself. Okay, let us start with the first part and see how we can find a solution to this. So when we look at this problem, we know that there are two charges. So let us visualize where these charges could be in space. We know that we have to find something or the total electric field at the origin. So this is our origin and this is the electric field that we need to find. Why the total? Because we have two charges, so the effect will be E1 and E2. So the first point is located at A, but this is in centimeter and we want to convert this into meters. So the point A is written in meters form. Why we are writing this? Because in the generic equation of the electric field, we get value of KQ divided by R absolute square into A of R, and here the value of K is 9 into 10 raised to power 9 meter per farad. So in order to have the same units, we are converting this centimeter into meter. So the value of A comes out to be 0.0, it comes out to be 0.25 meter minus 0.3 and 0.15. So this is in meter. Similarly, B gets updated to minus 0.1, 0.08 and 0.12 again in meter. So now we have these points. So if we want to plot these points, we can say that point A is located somewhere over here and point B is located somewhere over here. So B is having the points 0.25, and these are not to scale, by the way. So we can say that point A is having its effect over here and the electric field is in this direction. Point B is having effect on the origin and its effect is on this direction. So this point is our origin, because we want to find the electric field at the origin, and point A and B arbitrary are located over here. I can call this as the distance from A to origin with the unit vector AOA, and this point is the distance from B to origin with a unit vector of ABO. So this is my values with subscripts for the unit vector. So this is the effect of electric field 1 and this is the effect of electric field 2 coming from B and A respectively. So in order to solve this, I need to find the total electric field, which is by principle of superposition the sum of the electric fields available as per charges. So this is the basic equation or equation A which I have to fill in. So let us first start with finding electric field 1. So I'll change the color. So we start with finding E1. So E1 comes out to be charge Q1 divided by 4 pi epsilon naught, and then I have RAO epsilon naught square multiplied with the unit vector AAO. So this is the equation that I have. Let me call this equation 1. So in order to solve this equation, I need to figure out what is the value of the distance vector RAO. So let's start finding RAO. So RAO is the distance between A to origin, and we know the value of points for the coordinates for A is as such. So we can write its vector representation of the equation, and this comes out to be R of origin minus R of A, and this is, you basically subtract 0.25 with the origin, then 0.3 with the origin and 0.15 with the origin. So the value comes out to be minus 25. So this is R origin minus RA minus 0.25 into A of X, then you have plus 0.3 A of Y, and then you have negative 0.15 into A of Z. So this is the vector that we are getting. Similarly, if I take now the magnitude of this, so it comes out to be, you take the under root and square of the scalar terms. So 0.25 negative whole square plus 0.3 whole square plus negative 0.15 whole square, and it comes out to be 0.418. So this means my unit vector is now complete. So AAO unit vector is RAO divided by the magnitude of RAO, and if I incorporate the values, it comes out to be minus 25 A of X plus 0.3 A of Y minus 0.15 A of Z divided by 0.418. So we have all the needed values. Incorporate this. So then from equation 1, put everything into equation 1. The value of electric field comes out to be, so I'm going to write the final equation. You can double check if it's right or not. So it comes out to be 0.922 A of X, then you have minus 1.10 A of Y, and plus 0.55 A of Z and this all is getting multiplied with 10 power 4. So that's it. This is the electric field intensity of the first charge A going through the origin, and remember that the unit is volts per meter. So this is the first electric field intensity that we have found. Now we need to find the second field electric field intensity. Again, it is going to be in the same lines as we did with the first one. So for the second one, electric field intensity will be that we need to find E of 2, and the equation remains the same. So it is going to be Q2 divided by 4 pi epsilon naught R. R this time will be BO absolute square multiplied by A BO as the unit vector. So you need to find what RBO. So this is going to be you take the difference of origin minus R of B position vector, and you will get a certain value from here, and then you find the magnitude of this vector, so you will get another answer over here, and the unit vector will be ready. So I'll leave you with the answer of the second electric field E2, that comes to me as 8.38 A of x minus 6.7 A of y, and you have minus 10 A of z. Again, this whole term is getting multiplied with 10 power 4 volts per meter. So finally, once I have these two values, the total electric field from equation A comes out to be, so the answer, I'm going to write it over here in this box, and let us use the red pen. So the answer comes out to be, the total electric field comes out to be the sum of E1 plus E2, and it is 9.30 A of x minus 7.815 A of y minus 9.5 A of z, and this all is getting multiplied by 10 to power 4 volts per meter. So this is the answer which I am getting, and I am hoping your solution will be the same as mine. So this was an example giving us a further understanding of the idea on how to use principle of superposition to find the total electric field of system of charges or discrete charges. Let us look at another example. This time we'll just go over this example. It is in the same lines as what we saw previously. So in this example, we have given a charge 1 microcoulomb at the origin. So this is the first charge, Q1 of 1 microcoulomb at the origin, and its value is, and then we have another charge of 2 microcoulomb at this point. So this is point P with the value of 2 microcoulomb, and we have been asked to find the electric field at point Q over here. So this is the electric field that we need to find, or the point we need to find the electric field. And then once we find it, the second part of the question, so this is now the second part of the question, is basically asking us to find the total force when the charge of minus 0.5 is available at point Q. So how to go about this? Again, we need to use the principle of superposition, which means we need to find the total electric field as a combination of the two electric fields. So use the example which I did earlier and then apply it over here, and let us look what is happening. So we have defined one distance vector from origin to Q as ROQ and from P to Q as RPQ. Again, in the equation, we are going to first find ROQ and RPQ by the distance vector. So the ROQ gives us the distance of 645 because we are using the value of origin as a distance from 645. Then per RPQ is going to be the value of P minus the value of Q. So Q minus P is going to give us the second value, which is 6 minus 6 and 5. So the position vectors are found. Once we have the position vectors, we take its magnitude, and then the unit vectors are given as such. When all these things are found, we start with the first electric field. So we call this E1, and we use the equation of kq by r absolute square into a of r, where r square is the distance vector and this is the unit vector expression. So the value of E1 comes out to be volts per meter over here. The second comes out to be this one, so this is, let's say, E2. So the total electric field is the sum of E1 plus E2, which is this value. So this is the solution to the first part. Now for the second part, once we know the total electric field, which is EQ over here, we just use the basic equation of electric field intensity, which is the ratio of force per unit charge, to find the force which is going to be QE. So the force applied over here based on the value of charge of negative 0.5 microcoulomb comes out to be this micronewton. So this is the total force or the solution to the second part over here. So this concludes our today's lecture, that was on electric field intensity. To summarize, we found the electric field intensity equation for a point charge, and then we found the electric field intensity equation when we have system of charges. So to summarize, if we have system of charges, this is the equation that we are going to use, and if we have a point charge, then we are going to use this equation. See you in the next lecture.